Good morning, everyone. I'm Preetham Rajkwa. I'm a research postgraduate student in the Hong Kong University of Science and Technology. I'm working in the Artificial Intelligence Lab under the supervision of Professor Feng Jian Lin. The title of my presentation is VIAP Automated System for Verifying Integer Assignment Program with a Loop. Here is the overview of my presentation. I'll start with the objective, then I'll explain the main contribution of the paper, then I will explain the traditional way to prove the correctness of the program with a loop. I'll give a brief overview of the translation which we have adopted, and I'll give a brief description of the VIP architecture and followed by proof strategies that we have implemented in a VIP, a comparative study with the other automated verifiers, then partial and the total correctness, followed by the conclusion and the future work. In computer science, how to represent and reason about computer program have been a major concern since the beginning, as programs are some most complex man-made systems. So in our research work, we'll consider the program as an agent with knowledge base. Then we'll translate the program to a set of first-order enzymes, and which will give us a complete formalization. The main contribution of the paper, VIP implemented the algorithm to automatically translate a computer program to a first-order enzymes. Then we extend the translation by solving the recurrences generated during the translation. VIP automatically proved the partial correctness of the program given pre and post condition by mathematical induction with a Z3 as a basic prover without using the looping invariant. Whether our system can be used to generate looping invariant is a very interesting research question, as well as one more interesting question is whether loop invariance can be extracted from a proof in our system. But our current work is not giving emphasis on that. VIP can prove the correctness of the program without generating looping invariant, unlike existing work in the literature. And we validate this claim by showing the VIP can successfully prove a set of benchmark programs used by the loop invariant generation tool in the literature for the validation without requirement of generation of those looping invariant. And VIP is a fully automated tool which point to a new way of proving properties about the program. How to prove the correctness of the program with a loop? The traditional way, for imperative and non-concurrent program that we are considering here, notable approaches include Dijkstra's calculus of the weakest preconditions, then Horner's logic, dynamic logic, separation logic. For most those parts, these logics provides a rule for proving the assertion about the program. In particular, for proving the assertion about iterative loops, these logics rely on what have been known as the Horner logic, the Horner invariance. First, consider the partial correctness. The loop may not terminate, but if it does, the post condition will hold. To prove the post condition Q of a program with a while loop having a loop condition B and a body S with respect to a precondition P, first and foremost important step is to find out a suitable loop invariant INV. And it needed to satisfy two properties. Loop invariant needed to be initially true before the execution of the loop. Then it preserves its property means it remains the same during the execution of the loop. And then loop invariant and loop exit condition will imply the post condition. The study of the invariant have been a major research area since 1970. There have been large amount of work on automated discovery of looping invariant using static and dynamic analysis. Few mentionable works are InVGen, then DIG, Daikon, and Alligator. In this paper, we'll consider a class of imperative program composed of integer assignments, sequence, conditional statements, and a loop. And here is the grammar that our tool supported. In this paper, we propose so now basically in this way we're proposing a method to translate it. Basically, what did translation give us? We propose a way to translate a first order theory, which is a quantification over the natural number, which provides a relationship between input values and output variables. And the relationship between the input values and output values of the program variable will be completely independent of what we want to prove about the program. That gives us some more flexibility. So now move to the translation. Let's consider these two sequential statements, x equal to x plus y and y equal to 2 into x. So these two sequential statements can be captured by these two oximes, where x and y denote the initial value of the corresponding program variable, and x1 and y1 represent the value after the execution of these two statements. So now the obvious question is how the same can be done for the loop. Here the quantification over natural number scenario comes. It translates a program to a set of first order oxime by introducing for each loop a natural number term that denote the number of iterations the loop run before it exits. So basically it generates this following two formulas for a loop condition. N is a natural number constant denote the number of iterations that loop run before it exits. The formulas C small n denote the true value of the condition at the end of the nth iteration, and C began a formula that denotes the true value of the condition C at the nth iteration when the loop exits. When the loop exits, the loop condition will be complement of it. So now try to apply these rules. When we try to apply this translation rule in this example, so what will be the output? From this oximes, it shows that the value of m haven't changed during the execution of the program, but the value of x is depend on x. So if the loop do not execute, then the value of x remains same, and if loop execute, the value of x1, which is the final value of the final value of after the complete execution of the loop, execution of this program, is represented by a function of xn, and x and small n represent the value of x after nth iteration. So This program can be translated to the set of enzymes, the following set of enzymes. Here is the architecture of Z3. The front end deal with the it basically accept the program as an input, then translate into a first order enzymes, then it will try to solve number of recurrences if possible using Mathematica and SIMPy, tools like Mathematica and SIMPy. Then it passes the first order enzymes to the backend, and which translate these first order translated enzymes to a Z3 computable enzymes, then and proof engine and apply different strategies on those enzymes to and try to prove the post condition, and depend on the results will output whether system was VIP is successfully able to prove that post condition or not. Now let's move to the proofs strategies that we have adopted to prove the post conditions. And we use the Z3 to prove the properties about the program with enzymes generated by our translator. Given that Z3 accepts the first order enzymes, it seems to be a straightforward task. The problem is, of course, the theorem proving in the first order logic is undecidable, and there are many limitations in what Z3 can prove. So here is a small example how first order enzymes are represented in the Z3. Our generated enzymes are represented in the Z3 format. Enzymes in the Z3. This can be represented by this enzymes in the Z3. And the second issue is G3 was find it difficult with the enzyme of the format 2 generated, equation 2 generated during the translation of the loop, which is very crucial for our examination of the loop. So our strategy add the consequence 2 to the following set of enzymes. These equations we added along with the other enzymes. And then one more strategy is that most of the programs are non-linear in nature in our benchmark, and they have generated a number of exponential expressions. So we find it that Z3 is built-in module to handle a non-linear recursive arithmetic is too weak in the most of the time. Instead, we define our exponential. We'll define exponential function and try to convert our exponential terms into a function of this format, which will help Z3 to find out the answer. To illustrate how our system works, let's consider a program for computing the square root of a given non-negative integer x. So here's the program. To prove the correctness of the program, we need to prove this following post conditions. So after translation, we have the set of enzymes where A3 is a temporary function introduced and sent by the system and denoting the value of A after our nth iteration of the while loop. Similar convention can be applied to X, T, S, U and their subscript version. And the constant n was introduced to denote the number of iteration of the while loop before it exit. The variable and range over the natural numbers and universally quantified. So after you can see a number of recursive equation is generated during the translation, we can find out the closed form solution of these recursive equations, and once we find out, we'll substitute and we'll eliminate the temporary functions, and which will produce this following set of enzymes. So from those set of enzymes, we can translate it to a Z3 computable enzymes, and to prove this post condition, we'll add this enzymes and query Z3. If Z and Z3 will return us unset, and we can and successfully say that we can say that successfully VIP is successfully able to prove the post condition. Similarly, other post condition can be proved. Now the obvious question is, it is not always possible to find out the closed form solution of all the recursive equation that is generated during the translation. Then what we're going to do? Well, the strategy 2 is about that. So here we illustrate how our system work on the scenario by considering a program which implement a well-known Cohen's integer division algorithm. Here's the program, and to prove the correctness of this program, we need to prove these following post conditions. So after finding the closed form solutions and eliminating the terms for which we are able to find out the closed form solution, we'll have this set of enzymes, and you can see that a number of recursive equation where we are not able to find out the closed form solution. So to prove the post condition in such scenario, what we're going to do? So let's consider that this post condition x equal to q1y and r1. As we know that q1 and r1 denotes the output value of q and r respectively. So under the post condition, x greater than equal to y and y is greater than 0. For the above Cohen division program, first VIAP convert the post condition into the following assertion by substituting this value. So because we know that x1 can be substituted by this function s7 of n2, and r1 can be substituted by r7 and 2. So then our system would directly try to pass the Z3 and try to directly prove this conclusion, but it failed. So then in such scenario, we'll try to prove the post condition following by adopting a induction on the small n, because we know this value and constant value n is only dependent on the quantified variable v, and where our system is successfully able to prove this post condition by using an induction on over small n. Now let's move to the comparative study section, and we have compared our work with the 5 state-of-art verifiers, automated verifiers. Automated system means a system that verifies program with only pre and post condition along with the program given as a user input, which is written in some programming language. So now Leon, which is a stated verification system for a pure functional subset of for Scala, and later it is extended to include imperative program by translating them to internally pure functional programs. Then SMAC is also a self-contained software verifier, also a modular verification tool, and one of the achievement of the SMAC is it have scored the second highest overall score and win the silver medal in the SBCom 2017 competition. And the Seahorn is also a fully automated analysis framework for the LVM based languages. It is based on the constraint based horn clauses technique, and L2S is a static analysis and verification tool for the program which is built upon a C prover infrastructure which implement an incremental boundary model checking and invariant generation techniques and key induction. And Ultimate Automizer is also a model checker designed for a C program which proves the correctness of the program by computing the inductive invariant from the interpolation. So basically here's the experimental result, and we find that our tool for this 29 set of benchmark programs are performing much better than those tools, and among those tools Seahorn, and is among other tools which are other than VIPs. Seahorn is able to prove more number of programs compared to other tools. On partial correctness and total correctness, typically VIP proves the partial correctness of the program with respect to the post condition, pre and post condition, and this is because by introducing a natural number term to denote the number of iteration that and a loop run before it exits, we assume that loop terminates. Otherwise, contradiction will arise. Consider the following program, this program, and VIP can translate it this. VIP can translate this program to the following set of enzymes, and you can represent those enzymes in G3. The following, when you pass this set of enzyme to G3, G3 will return as a model and indicating that the set of enzymes are consistent. And otherwise, contradiction might arise and it will return unset. And now, if we add these two statements, and query Z3, and Z3 can entail those following statements, and this means that it can terminate only with the values when x is equal to 1 or x is equal to 0. So this is one of the interesting research direction. We are working on it, and which is not included in the current version of the VIP. In conclusion, in future we try to expand our system by adding more advanced heuristic to handle more complex programs. Here I conclude my talk by thanking all the program committee members for giving me the opportunity to present my work, and thanks for listening.